pi over 2 domain walls. And then we can again look at the local slopes and scale in. And now you see this exponent combination here goes clearly to a value less than 2. So that means that it's the second option that holds. We should actually replace the longer length scale by L. And that also then gives us a prediction for what this ratio is, and it's around 0.72. So this demonstrates explicitly that we have two length scales, and it also gives the ratio of those two different exponents. Okay, now let me come to the issue of why we call this deconfined quantum criticality. Well, we should maybe ask Leon if we really want to know why it's called that, but to me it has something to do with deconfinement of spin-ons. And spin-ons, as you know, are excitations of a magnet carrying spin 1/2, in contrast to, for example, magnons which carry spin 1. So if you look at the nature of the magnetic excitations, if I have this kind of cartoon picture of a valence bond solid, now I want to excite it. I can do neutron scattering, for example. I imagine, I cannot do it, but I can imagine that somebody can do it. Send in a neutron and flip some spins and make a spin 1 excitation. Okay, let's make a spin 1 excitation here. I take a singlet and I broke it up into two, let's say, up spins. And okay, now these are not localized. They can move about because of the Hamiltonian of the system. And, but you see, if I want to separate these two, we can think of these as spin-ons now. They each carry spin 1/2, but you see that they leave between them a string, what's called a confining string. So it's a string of valence bonds which has a mismatch to the neighboring rows of valence bonds. So this costs energy. It's like an elastic band. So this is also the physics of quarks. There's some very nice analogies actually to quark physics, and in fact we are now collaborating with some high energy physicists to really explore the analogies to quark confinement here, but I don't want to talk about that today. But anyway, if we have a valence bond solid, the point is that these spin-ons are confined to each other. They are bound to what's often called a triplet. Okay? So they can fluctuate about, but they cannot really go very far from each other. Now, then you can imagine as you approach the quantum critical point where this valence bond solid order goes away, that also this confining string will weaken. There will be lots of fluctuations here between, and it will not cost so much energy. So this spin-on pair can become larger and larger as you approach the critical point. And as you get to the critical point, these spin-ons should be liberated from each other, and then you can really think of them as the elementary excitations of the system. Okay, but now we can ask, what is the size of the bounce pair of the spin-ons? So according to the theory, the bounce state of the spin-on should be governed by the longer length scale, not the shorter length scale. And I think that's why you should call it deconfined criticality, because the length scale on which these deconfine is very, very large. Even when you are inside the valence bond solid phase, when you get close to the critical point, in practice it may look like you have free spin-ons. Okay, so the theory predicts maybe that this size of the bound state should be governed by the longer length scale, but actually if I read the papers it's a little bit unclear. So there's also some statements that the bound state is between these two length scales, and if I ask the authors of the paper directly, I get conflicting results. So I like all of them very much, but I don't want to say who is right. But one of them told me that yeah, it should be this one, and the other one told me no, it should be this, and he gave me some prediction, and I forget now what Leon said, but we can ask him after. But this is one reason why we really need to do numerics and see what's going on here, right? Because even if the papers are very beautiful, they don't tell us everything. Okay, so now this is based on the valence bond picture, right? And it's a very compelling picture, and actually we can also carry out simulations in this basis of valence bonds. And I know I'm running out of time, but Leon also went a little bit over, so I can as well. Although it's worse to intrude on your lunch break than the coffee break maybe, but anyway, let me spend maybe 5 more minutes. So we can carry out simulations in this basis and actually answer these questions. So But I'm not going to be able to do it very carefully. But the point is that we can actually do projector quantum Monte Carlo in these spaces. We can start with some state, and then we can act with some operators, which still just do some reconfigurations of these valence bonds and so on, and then we can do it from the left and the right, and we can measure some expectation values. And the nice thing is in this valence bond basis that a lot of observables are very easy to extract based on what's called transition graphs. So if we get the projected state on the left and on the right here, and if we just superimpose them, you see, so this was a 1D system, here I show a 2D system. We get some loops. And those loops basically contain all the information about correlation functions and so on in the system. Okay, let me skip, well, there's just some technical details of how we do it, but this is the main part, that we get these transition graph loops. Now this was in the sector of spin zero, the singlet sector, where everything is paired up into valence bonds. If we have spin-ons, we will break some bonds, right? We go to some higher spin sectors. So we can actually generalize the valence bond, it's pretty much the picture and movie I already showed you, to higher spin states. So we just get, so here is again just a simple 1D chain with 6 spins. If we have singlet, everything is paired up into bonds, and I get these transition graph loops. Here I just got one loop. If I have an odd number of spins, I can also look at the spin half state. Then I get one unpaired spin in both the bra and the cat. But they don't have to be at the same location, because these states are highly non-orthogonal. But instead they will be connected by a string in some sense, and there will be some loops. If I go to spin 1, I actually have 2 strings, but in this picture here, the 2 spin-ons here just happen to be on the same side, so the length of the string is 0, but there I have a string. So these strings actually, you can say, represent the spin-ons. So if I just look at one of the states, I have bonds and an unpaired spin. For example, if I have a spin 1/2, but if I look at the transition graph, I have it's double, because I have one in the bra and one in the cat. So you should think of the whole string as the spin-ons. Okay, so then we can look at the properties of these strings. That's the main point. And it's nice to maybe look at the movie here. So here is a movie that Xiaohui made of the spin 1 state. She took an open boundary system just to make it easier. Normally we do periodic boundaries, but just the movie looks nicer if we do open boundaries. So here you can see we have these 2 strings which represent the spin-ons, and they are drawn in different colors, so you can distinguish them. So this is actually deep inside the valence bond solid phase. You may not actually be able to see clearly a columnar pattern here, because there's a lot of fluctuations, but it is, if you measure the valence bond solid order parameter, it is formed here. And I think you can see that these 2 guys are somehow bound to each other. They don't go too far from each other, but although the bound state is already pretty large. If we go to the critical point, then these strings become very long, which actually means that the spin-ons themselves start to be ill-defined as particles. They cannot really be well localized anymore. They are actually not far from point particles now. But they start also not to care about each other so much. So they move about pretty much independently. These strings just evolve here. So quantitatively now we can look at, we can make some measure of how close these strings are to each other and define the size of the spin-on bound state. And we call that lambda, and if we divide lambda by L, we again have a dimensionless quantity, so we can actually do the kind of analysis I showed you before, and we can extract even the critical point just from looking at the spin-on bound state size, and it agrees with what we got before. But above all, we can look at the length scale associated with that. So we can do again this trick with slopes and so on at the crossing point. And we can see that we actually get a number for the exponent which is pretty, quite a lot larger than what the correlation length was. So this shows that we have this confinement, deconfinement aspect, that the length scale associated with the spin-on bound state is the larger length. And this is what we get for the ratio if we use the correlation length we got before, and that ratio and this value here. So now we can compare that with what we got from the domain wall calculation, and you see they don't agree completely, and we need to improve the calculations a bit, but they are still within 2 error bars. They are consistent with being the same scale, but in particular this one we would like to improve. Okay, but now I don't really have much time, but I can just say that I told you that the domain wall energy is scaled in a way which contain both these length scale psi and psi prime. Now it turns out that there has been some challenges in understanding certain quantities, and some people have proposed that the transition is actually first order based on behaviors of certain quantities that don't seem to fit in the standard way of finite size scaling. So there's a group of people that have decided that this is just the first order transition and just forget it. And other people like myself, we have tried to understand this as some kind of unusual but not impossible scaling corrections. So the question is it anomalous scaling or first order? Well, so what we believe now, based on this two-length scaling, is that actually we have a new paradigm for quantum critical scaling with two-length scales. That somehow it goes a little bit similar to what I discussed for these domain walls. We have two-length scales, and we have to write down some scaling functions. And an important issue is what factor we have for the size dependence. So for some quantity that scales like this in the thermodynamic limit, there's some overall size dependence at the critical point, and then there's something describing the behavior away from the critical point. And now one basically has to be consistent between the thermodynamic limit and the finite size scaling. And since I don't have time, I cannot really tell you how it works, just that there's a conventional way of doing that, and there's another way of doing that which apparently nobody looked at before, but they lead to two different predictions for the size dependence at the critical point. So this would be for the spin stiffness, the normal behavior, and in our case, in the new way of doing it, we get the exponent modified actually by the ratio of these two exponents. And everybody thought that this first here, that is set in stone. You cannot somehow violate that, but we believe that we can, because actually now we have determined this ratio in a different way, and we can just test if things work. And let me just show you the result. This is unpublished. Just how L times the spin stiffness in the conventional scenario, that should just be completely flat. But the data is not, and this is what people interpreted, some people interpreted as a first order transition. But now we can actually fit it if we just use that exponent ratio nu over nu prime that I told you before, which then would come in there. 1 minus that ratio, this would be. So we believe that actually this is the explanation for all the weirdness that was going on there. And in the process, we believe that we have a new type of finite size scaling that people had not considered before. And just let me skip the conclusions, but just say that finite temperature, if you do quantum criticality and field theories and so on, finite temperature corresponds to the thickness of the quantum system in imaginary time. And to get finite temperature scaling, one has to do a kind of finite size scaling. And we believe that also that is affected by this exponent ratio that we have decided. So a lot of temperature scaling forms will also be modified by this exponent ratio. And that's of course experimentally important when you look at thermodynamic properties and so on. So sorry for going over, and thank you very much.
Just very nice questions. Is there any special or reason that this kind of transition has two-length scale? For example, just for the confinement transitions, or any kind of, is there any other examples?
Right, so I'm not sure if it's sort of very straightforward to see it, but the basic example is these classical clock models. You know, if you take an XY model, for example, and restrict the spins to only point in certain angles like a clock, like, you know, 4, 10, whatever clock angles you have, then it's known that if this number of angles is large enough, the critical properties of the system are still, you know, given by the XY universality class. But it's also known that there's this larger length scale, which is exactly the size of a domain wall. And the valence bond solid itself, you know, has these 4 ordering patterns, and you can kind of look at those as 4 clock angles. You can somehow write down a valence bond solid order parameter as a complex order parameter. So you know you have something in the complex plane, and these 4 ordering patterns are 4 specific points in that complex plane. But the system can somehow go between them, so you can consider other angles as well. And this was, I think, the intuition that made Leon et al. Suggest that you have this. You know, maybe Leon can confirm or deny, but I think the intuition comes from there. And these classical models are quite well studied, although surprisingly what I've been talking about here, this domain wall energy and so on, has actually not been tested. So we are actually doing that right now in collaboration with Inge Kao, actually doing simulations of these clock models to try to see if we really get these anomalous scaling behaviors also there. We don't know yet, but I think that's where the intuition comes from.
Yes. What are system that shows these 2, what do you think are proper experimental systems?
Yeah, of course, that's a great point. So as I mentioned, the model itself that I talked about is intended to test the theory, but of course it would be very nice if we had some experimental system which you know, has a valence bond solid state. And I think there are some organics that people propose have valence bond solid states, but in general it's very difficult to see such phases if they exist because of disorder and all kinds of things. So there are systems where there's a lot of disorder where people talk about valence bond glasses, where somehow you have these bonds, but because of disorder they are not completely regular, they change. And you know, I forget the names of these compounds, I have to admit, but there are some cases like that. And one experimental, maybe a bit speculative, but I mean, this has been proposed by Sudhir Sachdev and others, that this deconfined criticality is related to certain behaviors in high temperature superconductivity. So I sort of believe myself that if you dope this JQ model, even at very low doping, it may show as a function of Q over J, you may be able to tune the different phases that you see in high temperature superconductivity. Maybe, at least that's something we are going to test. But it would be very nice to have an experimental valence bond solid and something that you can use. These dimerized models that I talked about in the beginning, there's a very nice experimental realization of a 3-dimensional dimer network, namely thallium copper chloride, which as a function of pressure undergoes a transition from this singlet phase to an L phase, and there's a lot of activity in that.
Okay. Any further questions or comments? If not, let's thank Professor Sandvik again. We'll have a lunch break until 1:30.